Morning. Today we will study policy gradient, which is a little bit different from a couple of previous times. So far actually we studied deep Q network, right? That is called value-based reinforcement learning. This one, value-based RL, deep Q network. Because the Q value is actually tries to evaluate how the current pair of state and action are good, right? Value is the same. It tries to evaluate how is the current state is the good, and the Q function tries to evaluate how is the how much the current pair of state action is good. So that is called value-based reinforcement learning. So far we studied that one. But why we start with value-based reinforcement learning? There are several reasons. The first one is mathematical foundation. The R is from Bellman equation, right? RL is based on a Bellman equation. It proves a recursive structure that is easy for a computer to optimize, and so it is actually a little bit easier to just simply implement Bellman equation with value function estimator or Q value function estimator. And explicit goal, by learning the worth, Q value of each action, the agent simply picks the one with the highest score. That is called greedy policy, right? We perform argmax on the estimated Q function to get the optimal action from the current state. That is very simple, right? Just simply taking argmax. That is all. And it is efficient in discrete space. Discrete means the number of action is not infinite. We have a limited number of actions. So discrete action space, like going right, going left, or the cardinal assignment of, or the going right, going left, forward, backward, this kind of discrete space, not continuous space. In discrete action space, it is highly effective for environment with a limited number of actions, like Atari game. So we started with value-based RL using deep Q network, but we tried to shift from value-based network RL to policy-based reinforcement learning. So actually these days, almost all RL algorithms are using policy-based RL, right? The combination of policy and value-based one, like an actor critic. So we try to shift to policy-based, in short PG. Despite the success of DQ network, it faces critical limitations in complex real-world scenarios. The first one is continuous action space. So in Q function, we from state we pass that to network, and then we estimate Q for all possible actions, right? State, action 1, Q, action Q, right? And then we just perform argmax. That means the number of the actions are discrete and number of action is not infinite, right? But in continuous action space, for example, just rotate your wrist about 30 degrees or rotate your elbow by 60 degrees. There are many infinite number of actions, so that we cannot design our network to produce Q values for all possible actions. So that is some limitations when we try to apply deep Q network to complex real-world environment. Most of the real-world problems have continuous action spaces. So deep Q network must compute max Q, which is nearly impossible when actions are continuous. For example, precise robot joint angles. And policy gradient avoid this by directly learning the action probability. And the second one is stochastic policies. So here where is it? Yes, we simply picked highest score, right? In the previous value-based RL, we simply pick an action with the highest score. That is deterministic, right? There is no randomness. When sampling action, we do not sample action actually. We just pick an action from estimated Q value. There is no stochastic stuff when we picking an action from estimated Q functions. But we try to introduce stochastic policies, stochastic action sampling. So value-based methods are inherently deterministic. However, in games like rock, paper, scissors, or alias environment. We will study this example later. An optimal strategy must be stochastic to avoid being trapped. So that we also try to shift to policy-based RL, and the final one is better convergence. Q values can change drastically with small parameter updates, leading to oscillating. Policy gradient changes the policy smoothly, offering more stable convergence. These two are primary reasons why we try to shift from value-based network to value-based RL to policy-based RL. And so we actually, so far, we approximated the value or action value functions using parameter W, right? Using deep network instead of computing all possible Q values or all possible value functions. We just try to approximate the value or Q value functions with learnable parameter W. A policy was generated directly from value function, for example, using epsilon greedy or taking random action. In this lecture, we will directly parameterize the policy, and we typically use theta to show parameterization. So instead of using this kind of estimator, now we shift to policy-based estimator so that it simply takes state, right? It simply takes state and outputs probability. Probability for all actions, right? That is very different. The previous one, value-based one, tries to estimate the expected summation of reward or expected summation of Q functions, right, in previous times. But here, now, we try to shift to policy-based one, which simply outputs probability for all actions. So goal is to find policy pi with the highest value function V pi. That is true, right? We try to find the policy. Policy is a pi which takes state and outputs action. So goal is to find the optimal policy pi with the highest value function. That is true. We'd like to maximize our value functions. We'll focus again on model-free reinforcement learning. In this class, we will always study model-free reinforcement learning. All the DQ network, all algorithm we will learn in this class belongs to model-free RL. So we will still study model-free RL, but the difference is that we're trying to shift from value-based RL to policy-based RL. That is the difference. So let's clarify what value, Q value, and policy are. The value function, we learned this one, right? It takes state as an input and outputs expected total reward an agent can accumulate starting from a state S and following policy pi thereafter. It represents how good it is for the agent to be in a particular state, right? State. So input is state and tries to evaluate how much the current state is good. The value function tries to estimate that one. And Q value function, the philosophy is the same. It tries to evaluate current input, but it tries to take action additionally, right? So the Q function action value, denoted by Q. The expected total reward starting from state S and taking specific action A, and then following policy pi. So it captures specific worth of an action in a given state. That is different from a value function. Value function only tries to evaluate current state, while Q value function tries to evaluate a combination of a current state S and then a specific action A. In value-based RL, like DQN, we pick an action that maximizes this value. That is what we, in epsilon greedy action sampling, that is what we did, right? Just from estimated Q value functions, we just perform argmax to get optimal action from current state. That is what we've done so far. So now we try to shift to policy-based ones. So policy is often denoted by pi. So it takes state pi, and then outputs probability of actions. A mapping from state to a probability distribution over actions. In policy-based RL, we directly parameterize this mapping with theta, neural network weights. The goal is to directly optimize the parameters theta to maximize the overall value V theta. So we try to clarify what the difference between value, Q value, and policy. But these three things are very important, actually. This is actually what we are trying to study in this time. So definition is a mapping from state S to a probability distribution over actions. That means the action could be discrete or continuous. In discrete space, we can use softmax, right? We can use softmax like we do in image classification. We can try softmax to get probability distribution over actions. But in continuous action space, we can use Gaussian policy. We can use Gaussian to get probability distribution over actions. We will study later. And in policy space RL, we directly parameterize. So the goal is actually almost the same. This kind of Q value or value, we actually try to optimize neural network, right? Neural network, because we cannot compute exact value and Q value functions. So we try to approximate it with neural network, which takes state and outputs value or Q value function. So this is the same. So our goal is to simply optimize neural network weight data. But the difference is it takes state and outputs probability of action. They just estimate value or Q value, while the output here is probability. That is difference. And the goal is to directly optimize the parameter data to maximize overall value V data. It's actually a little bit weird, right? So here, when optimizing value and Q value function, our objective function and what we can do is identical. What I mean is that, so here the goal is to maximize this one, right? So that we can perform some gradient ascent. We can perform gradient ascent with the output of these functions, because our goal is simply maximizing the output, right? Maximizing the output. But here, the output is probability of actions, which is different from V theta, So when in polar space RL, the output is probability of actions, which is different from V theta. V theta, it tries to evaluate how much current state is good, right? But here, it tries to just simply produce probability of all actions. So what we can get is probability of actions, but then what we want is maximizing V theta. So what we can get and what we want to do is different in polar space RL. In this value or Q value function, what we can get and what we try to do are the same, just maximizing the output, right? In a smart way, right? But here, polar space RL, what we can get is probability of actions. But we are not trying to simply maximize probability of actions. What we want to do is maximizing value function. That is difference. What we can get and what we try to do are different. That is it makes a polar space are a little bit complicated. So we study value-based RL. Here, value-based RL is here, right? We have learnable value function, but on policy, as I said, policy, state, action, that is policy. We do not have explicit policy. We do not have explicit policy function. We just simply, from learned value function, we just simply perform argmax, like an epsilon gradient approach to get action, right? So we just have implicit policy, not explicit policy. But here, policy-based one, today's focus, we do not have value function. Here, policy-based one, here. That is our today's focus. No value function, but we have learned policy. So we are trying to study how can we optimize policy function. Actor critic, which we'll study later, is a somewhere between value-based and policy-based one. Learnable value function and learned policy. That is actually what people today widely using. So this is our focus. Policy-based one. So it's actually very different, right? They are in a very opposite direction. Value-based one and policy-based one. We started with value-based one because in one sense it's easier. It's easier to study value-based one. But in real-world environment, they're in complex environment, value-based RL doesn't work. So today we shift to policy-based one, and then later we will shift again to actor critic. Anyway, this is today's focus, policy-based RL. No value function, but we have learned policy. So far we studied on deterministic policies or epsilon greedy policies. But now we are thinking about direct policy search in RL. We'll focus heavily on stochastic policies. Right? Deterministic means there is no randomness. From estimated Q function, we can simply perform argmax to get optimal action. But here, in policy, as I said, we simply output probability of action. That means there is always stochastic. From probability distribution, we need to sample action. That is stochastic, right? There is randomness. So we'll focus heavily on stochastic policies today. Let's take an example. Why value-based RL is not good in complicated environment, and policy-based RL could address this. This is called alias grid word. Alias means, so here the agent cannot differentiate the gray state. So here there are two gray states, right? That means it tries to, the meaning of this one is like cannot differentiate. It cannot differentiate. Cannot differentiate. So agent cannot differentiate these two gray states, let's say, and consider features of the following form. Phi, which takes state and action. It is 1 when there is a wall to the north direction. So this state, right? This state have wall in north direction, right? And then action is moving to east. Then we say this feature, just a feature, try to describe current state of the agent. And let's say our feature descriptor is phi. It is 1 when there is a wall to the north direction and current action is moving to east. And 0 otherwise. So compare value-based RL using approximate value function. Here it is 1. And the policy-based RL using parameterized policy. So we try to, this is what we studied so far, right? Deep Q network. And this is new one, policy gradient. So under aliasing, optimal deterministic policy will either moving west in both gray states, shown by red arrows, and move east in both gray states. Why this happen? Because agent cannot differentiate this one. Agent have the same feature descriptor. Agent think when agent is at state A and state B. Agent think when agent is state A, it cannot differentiate whether it is on state A or state B. And if agent is on state B, then agent cannot differentiate whether it is on state A or state B, right? So that the action could be the same because state is the same. Agent cannot differentiate these two states, let's say. Then the state will move to west or east, but because the state is the same. But here, then it tries to always move to west or east. West is shown in the red arrow in the above figure. Either way, it can get stuck and never reach the money. Here is the money, right? Value-based RL learns a near deterministic policy, greedy or epsilon greedy. So it will traverse the corridor for a long time. It will just oscillate this region, right? Because it cannot differentiate the gray states. It always do the same action. But how about stochastic policy? Although the agent still cannot differentiate the state A and state B, still agent cannot differentiate these gray states. But stochastic policy, let's say we have pi theta. There's a wall to north and the south, and then move east is 0.5, the probability. And then wall to north and south, and move west is 0.5. So that now we have stochastic, right? We have probability. So with the probability 0.5, the agent can go west. Or probability 0.5, the agent can go east. So that we have stochastic policy. And it will reach the goal state in a few steps with high probability. So that is the good point of policy-based RL. Instead of simply doing deterministic policy, given state, we have stochastic policy using this pi. That is a good point of policy-based reinforcement learning is, compared to the value-based reinforcement learning. Policy-based RL can learn the optimal stochastic policy. So now there are gonna be many mathematical equations, but what I want to say is very simple. Just that is today's focus. I will introduce this later. There are going to be many equations, but you do not have to be afraid. Policy-based reinforcement learning is an optimization problem. Find policy parameter theta that maximizes v, value function. We can use gradient-free optimization, but in many times we use gradient-based optimization, gradient descent. Of course, there are more advanced algorithms like a conjugate gradient, but we simply choose gradient descent in this class. Many extensions are possible, and a method that exploits sequential structure. So policy-based reinforcement learning optimization problem, that is true, right? We need to optimize the network weight theta, which is weight of our policy network that takes state, pi, and probability of all actions, optimize in a way that we can maximize v, right? That is our objective function. So let's define this one, policy gradient. What is policy gradient? So we can define a value function to make explicit dependence on the value on the policy parameter. And the policy gradient algorithm search for local maximum in V by ascending the gradient descent the policy with respect to the parameter theta. So when we optimize the policy network, we would like to maximize value function, right? So that we can try gradient ascending gradient with respect to parameter theta. So the difference parameter theta could be represented by this one. Alpha is the learning rate, and this is a gradient of value function. Although we do not have explicit value function, as I said, in policy-based RL, we do not have explicit value function, but let me just introduce this value function. So that is the residual of the policy network theta, right? We'd like to maximize value function, right? So this is simply policy gradient. The gradient of the value function is called policy gradient. It can be computed like this. And alpha is a learning rate. And here, the gradient of value function is policy gradient. And today's focus is how can we make a relationship between gradient of value function and gradient of policy function. In some way, if we can make a good connection between gradient of value function and gradient of policy function, for example, it turns out that gradient of value function is mathematically identical to the gradient of policy function. That is very good, right? Very good situation. In some mathematical way, if we can prove that this gradient of value function is same as the gradient of policy function, then we do not have, although we do not have access to value function, although we only have access to policy function, we can simply maximize value function with the output of policy-based network. That is a good situation for us. So actually, that is today's goal. How can we make a connection between gradient of value function, this one, policy gradient, and the gradient of policy network? And the conclusion is they turns out the same, but today we will see how can we drive these two are identical, and they have which connection they have. So maximizing values with this gradient is our goal. When optimizing policy function, our goal is maximizing value function. But as I said, all we can compute is just this one. All we can compute is just gradient of policy network, because we do not have value function. As I said, in policy-based RL, we do not have learnable value function. So what we can get is just, what we can compute is just gradient of policy function, as you do not have learnable value function, right? So how to drive this gradient of value function from gradient of policy network so that we can maximize value function during the training of the policy function. That is today's focus. This is today's focus. The conclusion is that, fortunately, they are highly correlated, and it turns out that just maximizing value function is same as the maximizing, the gradient of value function is almost the same as the gradient of policy network. That is today's conclusion. But fortunately, so that we can study policy-based RL. So let's assume policy pi theta is differentiable, where it is non-zero, and we can compute gradient. And recall policy value is this one. Let's say gamma is just 1. Discount factor is just a 1. So then we can say that the value is just expectation of cumulative reward, where the expectation is taken over for state action visited by pi theta, our policy network. And we can express this value function, policy value, in multiple ways. Like the first one is, it makes sense because as I said, this policy network tries to talk about probability, right? So expectation is just a summation of probability times the actual value, right? So that this is probability, the pi just produces probability, and Q is the expected reward, right? So that we can multiply them together and then add them, and then we can get this value function. Or we can rewrite this one in this form. Just P is a probability, and R is expected reward, where tau is just a state trajectory of state and action. And P tau theta is used to denote the probability over trajectories when executing policy pi theta starting in state S0. And R tau is the sum of reward for a trajectory tau. I mean, it is not very complicated. They are just the same. So this is what we studied so far from Bellman equation, right? When discount factor is just a 1, then the value function could be written like this. And then we just rewrite expectation with the multiplication of probability and actual value. And then we can get this one, and then we can rewrite this to this one. And then we will focus on later definition, this one. So first and second, we will study second definition, this one. And using second definition, our goal is prove that this gradient and this gradient are highly correlated. Our goal is to show that. So denote state action trajectory as tau, and use R to be sum of reward for trajectory tau. Policy is this is the same as the previous slide, where P tau is used to denote probability over trajectories when executing policy pi theta. In this new notation, our goal is to find the policy parameter theta, right? Policy parameter theta. Our policy network here, state pi prof, where this is parameterized with theta. So our goal is to find policy parameter theta, the weight of our policy network, which maximizes value function. Value function can be rewritten like this, so that is the same. So this is our objective. We'd like to find our policy parameter theta, which maximizes value function. Then we can rewrite this one, gradient of value function. Then value function is same as this one, right? This one. And then we can plug in gradient inside, and then we can make this one. We can cancel this to 1 so that we can add this. And then we can just rearrange these terms so that we can get P tau, R tau, and then this is likelihood ratio. So this becomes the same. And then, the gradient of L and X is 1 divided by X. It is high school. We learned this high school, right? So that if we have log P tau theta is P tau theta p tau theta. Based on this one, we can just use composite function differentiation, right? So that it turns out that the gradient of value function is this one. It's okay. This is just, you know this one, right? It's just a high school math. When we differentiate the log, then we can get 1 divided by x. And then, as I said, always find policy parameter theta, and then we can take gradient with respect to theta, and it turns out that the gradient is this one. And then we cannot compute all possible trajectories of action, so that we try to approximate it using m sample trajectories under policy pi. So that we try to approximate it with when m should be very large, then we can approximate this one with g hat. So that this one becomes this probability, right? And tau becomes the same, and then this one becomes the same, right? So let's say we approximate this one using m sample trajectories under policy pi, and the policy becomes 1 divided by m, and then we can sum them up, sum all the multiplication of reward and gradient, likelihood ratio. Of course, m should be very large, maybe. So far, good? Okay? Please raise your hand if you have any problems anytime. And approximate using m sample path under policy pi theta, so that we can get this one, right? And then we can decompose this one. From this one, the only complicated looking term is only this one, right? This looks easy, but this looks a little bit complicated, right? So that we'd like to decompose this one. We can, this one can be rewritten, p tau theta can be rewritten with this one, initial state distribution policy dynamic models. And then we plug into log, and then it turns out that the gradient of p, log p, is like this. Gradient of log pi without dynamic model. This is called dynamic model. Probability from state st to next state st plus 1. It turns out that no dynamic models are required to get the gradient of p, right? Because this is, there's no theta here. There's no theta here, so we can cancel them. And then that is what we can get, like this. And then this is, from lecture, this is from previous one, from slide 12. This is the policy gradient, and then our goal was how to drive this gradient of v theta from pi theta so that we can maximize value function during training of the policy function. That was our goal. And then now it looks interesting, right? We started with v. We started with gradient of v, and then using likelihood ratio, we change it to this kind of m sample pattern under policy pi theta, and then we decompose this one, and then it turns out that it looks like this one, right? So that now we can make some connection between gradient of value function and gradient of policy function. Now we can make a connection. So that, the goal of today's class was how can we make connection between gradient of value and gradient of policy. And now we can make a connection between gradient of value and gradient of policy, right? So that what this tells us to me. When training policy network, what we can get is just pi theta. We do not have this one because we do not have learnable value functions. But only from pi theta, by only optimizing pi theta, mathematically it turns out that it is identical as we try to maximize value function, right? That is our observation. So that we now mathematically derive that gradient of value function is highly correlated with the gradient of policy function. So although we do not have access to value function, we can somehow optimize policy function, policy network in a way that we maximize value function, although we do not have explicit value function. Actually, this is a very important thing. So, I mean, in policy space 1, although we do not have value function, we now can optimize the policy network in a way that we maximize value function. And score function, this is called score function. And maybe some of you guys have heard this score function in generative model. In diffusion model, there's a score function, right? It is mathematically the same. Although the meaning is very different, but mathematically the same. It is a score function. A score function is the derivative of the log of parameterized probability and likelihood. Example, let pi s theta be probability of state s under parameter theta, and the state score function would be this one. And for many policy classes, it is not hard to compute the score function. So, I mean, let's get back to where is it? Let's get back to here. So, I mean, if we have delta theta, then it's all. Well, our goal is finding delta theta so that we can update our network parameter theta. But to get delta theta, we need to get gradient of value function, which is called policy gradient, right? Then how can we get policy gradient? That is problem because we do not have value function. So that how can we get gradient of value? So we define policy value function like in this way, and then it turns out that gradient of value function is like this, and then we rewrite this one like this one, and then we rewrite this one into this one, so that now what remain is only this one, right? From this equation, we can get this. Only remaining thing is this one. And it turns out that this one is same as this one, score function. So our goal is getting delta theta, but it turns out that if we can get score function, then that's all. We need only score function to update our theta in our policy network. So how can we get score function then? That is not difficult, fortunately. As I mentioned in the earlier time of today, there can be a couple of policy. The first one is softmax policy. If we have discrete number of actions, if we have limited number of actions, then we can use softmax policy. For example, state and then pi. Like image classification, we have a predefined classes of actions, and probability is 0.2, 0.3, 0.5, 0. They are probability. That is softmax policy. For discrete action space, we can use softmax policy. Weight actions using linear combination of features. Probability of action is proportional to exponentiated weight. That is definition of softmax, right? Def of softmax. Using this one, we can just simply take logarithm and then we can just derivative, right? We can get derivative of it, like this kind of several steps. Now we can get score function. When we design our policy network to output probability of predefined number of classes and then use softmax as activation function, then our score function can be mathematically computed like this one. So this is the definition of softmax, and the score function is like this one. We can plug in this score function to this one. We can plug in our score function to here, here. Plug in the computed score function to here, and then we can get this one. We can plug into this one so that we can get gradient of value, and then we can plug into delta theta, so that we can get delta theta only from output of Polish network. It is very interesting, right? Very fortunately, without access to explicit value function, we can get score function from Polish network, and then we can, depending on the output of design of your Polish network, like if you use softmax policy, then we can compute score function, and then we can just plug in the calculated score function to here, and then we can get this one, and then we can get this one, and then we can get delta gradient of value function, then we can get delta theta. There are many steps, but the conclusion is that only with output of score, the policy function, we can get delta theta, so that we can update theta. That is softmax policy for discrete action space. And of course, there are continuous action spaces. In continuous action spaces, a Gaussian policy is natural. Gaussian policy is actually very widely used these days. Mean is a linear combination of state feature, and variance may be fixed or can also parameterize. So this is a very practical one. So variance could be fixed. There are maybe three options. The first one is we can use sigma as constant, or we can just sigma as a optimizable, and third one is output of pi. There can be some ways how can we. These three are actually widely used. Some people use constant. So state pi. So it can output mean. At the same time, it can output sigma. Most Gaussian Polish network outputs mean, but some Gaussian Polish network outputs this sigma, or some people just use sigma constant sigma without designing network to output this sigma, or some people just discard this one, and then sigma is the optimizable parameter for all inputs. So there are three options. But anyway, variance may be fixed sigma or can be parameterized. So policy is Gaussian. I think the variational autoencoder. It's very similar to variational autoencoder. Variational autoencoder VAE. It outputs mean and sigma, right? So using this one, what was this one? Like this one. We get policy. We get action like this kind of reparameterization tree. That is actually widely used in Gaussian policy network as well. So we let our policy network outputs mean of the Gaussian, and standard deviation. Standard deviation can be from output or optimizable or constant. Anyway, then that becomes action, right? I'm not sure this one and which one is correct. I'm not sure. But anyway, so that we can, as we did for the softmax policy function, we just, from this softmax activation function, we just simply perform the derivative, and then we can get score function of softmax policy, right? In the same way, we can do some derivative, and then we can get score function of Gaussian policy. This is score function of Gaussian policy. And deep neural network and other models where it can compute the gradient can also be used to represent the policy. So of course, VAE use K divergence, but here Gaussian policy do not use K divergence loss. But the mathematical formulation and how can we get output is almost the same as VAE for the Gaussian policy. It just outputs mu and standard deviation, and by combining them together, we get action, right? So that we can get probability of actions for continuous action space, and at the same time, we can make it differentiable, and then we can handle continuous action space. So these two are representative policy, softmax policy for discrete action space, and Gaussian policy for continuous action space. In both cases, we can easily get score function. And putting this together, the goal is to find policy parameter theta. Back to the first objective. Then our original goal was find policy parameter theta that can maximize V theta, right? We approximate this, so we made lots of derivative so that from this one, we approximate with the M samples, and then it turns out that we can just use score function of policy network. So we do not need to know dynamic model. We can just, what we only need to know is this one, score function. And then for score function, depends on your network, like softmax policy or Gaussian policy, we can easily compute the score function, and then we can just plug into the, here. We can plug into here. So that we can get gradient of value. From gradient of value, we can update data using data theta. Let's secure understanding. So given this one, we studied this one, right? Gradient of value function, we sample n samples, like this one, right? The likely ratio score function, policy gradient, it requires reward function that are differentiable. True, false? True, false? True, false? True, false? Make a guess. What's the answer for A? True? True, raise your hand. False? Yes, the answer is false. This is a gradient. This is only the thing that we only need to know. So, but if we get reward, it's non-differentiable, it's okay. Just we can compute non-differentiable reward, and then we can just plug in numbers into here. So that the answer is false. And B, can only be used with Markov decision processes. True? False? How about others? The answer is false. We do not make any Markov decision process assumption when driving this equation. For C, it's usually useful mostly for infinite horizon tasks. True? False? The answer is false. Because here, infinite means there's no, the number of m is, it means m is infinite. But here we need non-infinite m to compute this gradient of value function, right? So if m is infinite, we cannot compute. That is the reason why we introduce m. Without m, we can just directly use the this one. Where is it? Yes, we can just simply use this one. But as we cannot compute all cases, as we cannot compute all trajectories, we just sample some infinite m samples. So that is the reason why I introduced m here, so that it is useful mostly for infinite horizon task. False, because m should not be infinite. A score function gradient estimator. Let me introduce some intuition. Consider generic form of this one. G hat, which is so here, that is we've learned so far, right? Reward multiplied by the score function. And then we can just simply replace reward with some fxi. And this is just a p score function. Fx measures how good the sample x is, and moving the direction g hat pushes up to the log probability of the sample in proportion to how good it is, right? So it's valid even if fx is discontinuous and unknown, or sample space containing x is discrete set, right? So we do not take care about fx is discontinuous, unknown, or sample space is discrete set. We do not take care about it, right? The goal of fx, which is a reward, is measure how good the sample fx is. Sample x is. And here, moving the direction g hat pushes up the log probability of sample in proportion to how good it is, right? In proportion to, because we multiply fx. And that is the very famous theorem, Pauli's gradient theorem, a very famous one. So why this famous? So it provides a unified gradient form of various objective functions j, such as episodic reward or average reward, and express the gradient of overall performance as the expectation of the policy's score function weighted by action value q. Allows for policy optimization without requiring transition dynamic model of the environment. Suggests adjusting policy parameter theta to increase the probability of actions that yield higher than average returns. It looks a little bit complicated, but we've learned all the things today. Unified gradient form. So here, regardless of policy objective is episodic reward, average reward for each time step, average value, we do not take care about it. Just policy gradient can be policy gradient. There was this one, right? Can be this one. And fx, we learned this one, right? We learned this one. Fx measure how good state sample x is. And that is the role of q for the function, right? So we introduce q function here, and then this is the score function. Without requiring transition dynamic model of the environment. That is the model-free RL. For any differentiable policy, for any of the policy objective function, the policy gradient is like this. That is the very famous policy gradient theorem. So J is here. Where is it? Reward, right? J is a kind of reward. So it can be seen like a value function. So that is actually consistent. We learned today. From the gradient of value function, we made many steps and then successfully derived that the gradient of value function can be represented with the expectation of the score function. That is what Polish gradient theorem is saying. But unfortunately, Polish gradient is noisy in practice. We have typical pattern, right? We learn something, but unfortunately it is not good. So that we learn something, but it's not good. There's always typical patterns. This is also the same. We have the same pattern. Polish gradient, in theory, it looks good, but in practice, it's very noisy. Since the gradient is estimated using a limited number of sampled trajectory m here, the estimate G hat can deviate significantly from the true gradient. And the update rule uses total return, which is the sum of many random reward along a long path. Any small random variation in early transition can lead to massive swings in the final cumulative reward. And every action in the trajectory is scaled by the same total reward, R tau. This makes it hard to distinguish which specific action was actually responsible for a good or bad outcome. And the final one is Polish gradient only cares about the relative increase in probabilities without the baseline. Even a bad action that happen to get slightly positive reward will have its probability increase, leading to erratic updates. I just briefly introduced because next time we will study in detail why Polish gradient is noisy and how can we address such kind of noisy Polish gradient in two ways. Temporal structure, which is called capital reinforce, and second one is baseline. So there are two ways to fix this kind of noisy Polish gradient. We will study this next time. So today's focus was this one, Polish gradient theorem. From gradient of value function, we successfully derive it with the score function of the Polish network. That is today's focus. That is for all today, and any question?